So since 36 is 2 squared times 3 squared, there are 2 plus 1. Looking at that exponent gives you 3 different ones. 2 to the 0, 2 to the first, 2 to the second, times 2 plus 1, or 9 different factors. Which leads us to our next theorem. Our next theorem states that the divisors and factors of a natural number are all the powers of their different prime factors, all those powers added 1 to them and multiplied together. So suppose that a counting number is expressed as a product of m distinct primes and their respective exponents. Let's say their prime number 1 raised to the nth power, prime number 2 raised to another nth power, last prime number raised to some other power. Then you just take all those powers, add 1 to them, and that tells you how many different divisors there are. Just like there were 9 and 2 squared times 3 squared. So how many divisors, factors, does each of the following numbers have? This is a number whose prime factorization is 13 squared times 29 to the 5th power. So the number of factors is going to be 2 plus 1 times 5 plus 1. The quantity 2 plus 1 times the quantity 5 plus 1. So there are 3 times 6. If you listed them all out, this number would have 18 different factors. And you could list them out if you wanted to, but there they are, 18 of them. 120, well, in order to figure that out, we're going to have to find its prime factorization first. So I'm going to do a tree. It's 10 times 12, and 10 is 2 times 5, and 12 is 3 times 4, and 4 is 2 times 2. So 120 is actually 2 to the 3rd power times 3 times 5. And so if I figure out how many prime factors it has, I'll take the exponents of each. The understood exponent on the 3 is 1. The understood exponent on the 5 is also 1. So it would be the quantity 3 plus 1 times the quantity 1 plus 1 times the quantity 1 plus 1. So it's going to be 4 times 2 times 2. So this one has 16 different factors. So to figure out how many factors a number has, find its prime factorization, take the exponents of all the prime factors, add 1 to them, and multiply them together. Theorem says that there are infinite number of prime numbers. It keeps going on forever and ever. We listed some earlier. This theorem helps you determine whether or not a number is prime or if it's a composite number. If n is composite, then there is a prime, p, such that p divides n, so it's a factor of n, and p is less than or equal to the square root of n. So what you can do is you can find the square root of a number and check for any prime factors that are less than that. That's what we're going to do. We're going to take the square root of 101, and we're going to determine whether or not 101 is prime or composite by just looking at the prime factors less than the square root. So that's what we do. First thing we're going to do is we're going to find the square root of 101. 2, we're going to list as primes less than the square root of 101. And then 3, we're going to check to see if any of them divide. If so, it's composite. If not, it's prime. If none of them work, none of the primes less than the square root of 101, divide 101, then it is prime. That is what your theorem says. So you don't have to check a whole lot of numbers. In fact, the square root of 101 is approximately 10 point something, because the square root of 100 is 10. So I only have to check the primes less than 10, or equal to 10. 10 happen to be prime, but of course it's not. So I'm going to check 2, 3, 5, 7, and that's it, because 11 is more than 10, and I don't have to check 11. 101 clearly isn't divisible by 2. 101 is also not divisible by 3. You can just take it, check it, and see. One quick way to see if a number is divisible by 3 is add up the sum of the digits. The sum at 1 plus 1 is 2, and it's not divisible by 3. That's an odd test, but it works. Not divisible by 5 because it doesn't end in 5. So the only thing it might be divisible by is 7, so just check real quick. It won't go in there, though. 7 won't go into 31 evenly. You have a remainder of 3. So it's not divisible by 2, 3, 5, or 7. So since 101 is not divisible by 2, 3, 5, or 7, we say 101 is prime. And that's how you do the test. You can't just say to me that the number is prime. You're going to have to prove to me that the number is prime. And to do that, you need to list all prime numbers less than the square root of the number. If those numbers do not divide that number, then the number is prime. Let's do a couple more examples. Let's determine whether or not 439 is prime or composite. So the first thing I'm going to do is I'm going to take the square root of 439. It's 20 to 21, I would say. Let's just check here. It's 20.9 something. So it is 21. So I'm going to check prime numbers less than 21. I'm going to check for 2, 3, 5, 7, 11, 13, 17, and 19. And then we can just run through and decide which ones it's divisible by. It's not divisible by 2 because it doesn't end in 2. It's not divisible by 3. If you add up the digits, you have 4 plus 3, which is 7. 7 plus 9 is 16. That number is not divisible by 3, so it's not divisible by 3. And you can also not divisible by 5 because it doesn't end in 0 or 5. So we do need to check 7. You can do this longhand. 439 divided by 7. It's not divisible by 7. 439 divisible by 11. Nope. So 439 divisible by 13. Nope. 439 divisible by 17. Nope. Not a whole number. And last one, 439 divisible by 19. Nope. So it wasn't divisible by any of those numbers. So since it's not divisible by any of those numbers, what we're going to do is we're going to say 439 prime. Now, if one of those had worked, then that would be one of its factors, and so therefore it would be composite because it has a factor other than 1 of itself. I've got to give you some more answers here to your quiz. 2 more answers. This is for questions 3 and 4. What is my husband's favorite college basketball team? My husband's favorite college basketball team is Murray State, of course. And then the second question, what is my husband's least favorite basketball team, college basketball team? My husband cannot stand UK I'm sorry, folks, but he can't. He does not like them at all. Born and raised in Kentucky, but he is a Murray State fan through and through. All right, let's go on to section 4.3.